Hello and welcome again. This is the third video in this topic, turning effect of a force. In the first video, we defined the moment of a force. In the second one, I taught you how to calculate the moment of a force about a point. Now, in this video, we are going to look at a very important concept, the principle of moments. The principle of moments. And you can see, I've already written the principle of moments on this slide, and I want to explain certain points. But first of all, let's look at the complete statement of the principle of moments. The principle of moments states that if a system of forces is in equilibrium, so we are looking at one of the conditions for this principle to apply. For it to apply, the system must be in equilibrium. So if a system of forces is in equilibrium, the sum of the clockwise moments about a point is equal to the sum of the anti-clockwise moments about the same point. So the first thing you note about the principle of moments is this. You must state the conditions under which it must apply. And the condition is that the system must be in equilibrium. Most laws and principles, they always ask you to state the condition under which they apply. And this is one of them. So the condition to remember here is that for the principle to apply, the system must be in equilibrium. At this moment, I can mention, although I'm going to mention it later, that there are two conditions that must be satisfied for equilibrium, for a system to be in equilibrium. One of them is that the principle of moments must apply, and the other one is that the resultant force on the system must be zero. I've already taught you about a resultant force. So if you want to review how we calculate a resultant force, just play that particular video up there and it will remind you about how to work out the resultant force. However, those are the two conditions for a system to be in equilibrium. I will be talking about that second condition later on. For now, I just want to pay full attention to principle of moments. So, the other term that I want to explain here is the idea of the sum of the clockwise moments. It means, when you talk about sum, it means that we are adding two or more items. So it means if there are two or more clockwise moments, then you must add them in order to get their sum. So that is the second point that you must remember. Then all these moments are taken about a particular point. We do not change the point about which we take moments. We identify one point and stick to it throughout. It means that is the point about which all moments must be taken. So it means that if we have two clockwise moments, they are taken about a given point. And even when we come to calculating the sum of the anti-clockwise moments, the anti-clockwise moments must be taken about the same point. So as you struggle to recall this principle of moments, those are the key points which I'd like you to pay close attention. And in my calculation in this video, I'm going to start by showing you how to calculate sum of maybe clockwise moments or anti-clockwise moments in a system. So let's look at this first question here. We are given a grid. Again, the length of one box there is 1 meter. Just take it to be 1 meter. There are two forces. There are several points here. I think I wanted a situation where, let me just go back. I wanted a situation where I just want to take moments about point A. What is the moment due to the 150 Newton force about point A. It is 150 times 2 meters, 150 newtons times 2 meters, which will give me 300 Newton meters clockwise. What is the moment due to the 100 Newton force about point A? It will be 5 meters times 100 newtons, and I get 500 Newton meters clockwise. So you can see there are 2 clockwise moments about point A. So since there are more than one, then I add them. I have 300 plus 500, and I get 800. The sum of the clockwise moments about point A is 800 Newton meters clockwise. How about if I change the point about which I'm taking moments? I take moments about point A. 1 meter times 150 newtons, I'm going to get 150 Newton meters clockwise. 4 meters times 100 newtons, I'm going to get 400 Newton meters clockwise. The sum of the clockwise moments about point B will be 150 Newton meters plus 400. I get 450 Newton meters clockwise. I can go ahead and change the point about which I am taking moments. You can see that when I change the point about which I am taking moments, the sum of the clockwise moments, or whatever direction it is, changes. The other thing I want you to observe is this. When I take moments due to these forces about point A, the distances, all of them, are measured from the same point. This one was 2 meters. This one was 2 meters times 150. I got 300 Newton meters clockwise. Now, although this is 3 meters, let me just show you. Although this is 3 meters, and this is one of the tricks sometimes they use in the exam. They give you this distance, then they give you this, and ask you to calculate the moment due to this about this point. It's up to you to realize that when we are talking about moment due to a given force about a certain point, the distance must be measured from that point. So if several distances are given, for example, in this case, you have 2 meters is given and 3 meters is given, it's up to us to realize that the actual distance involved here is 5 meters and not just 3 meters. Understand that. That one is very important. Very important. Because they will try to trick you by giving you distances somewhere in the middle, but the point about which you are taking moments is somewhere else. So always remember to add those distances. To add the 3 meters, for example, plus the 2 meters here, and you get the actual distance. When we are using point B, the distance for 100 newtons force is 4 meters. It's not 3 meters, but 4 meters, because the distance must be measured from this point all the way to the line of action of the 100 Newton force. So, up to that point, you now understand how I get the sum of the moments about a given point. Of course, the sum of the moments about point C, the moment due to the 100 Newton force, will be 0. So the sum of the 100 Newton force and 150 Newton force about point C will be contributed by the moment due to the 150 Newton force only. So the sum of the moments about point C will be 3 times 150, which is 450 Newton meters anti-clockwise. When we come to point D, I will get 3 plus 2, that is 5 times 150, where I get 750 Newton meters anti-clockwise, plus this will be 200. So I get 950 Newton meters anti-clockwise. If the moment is taken about point D, I'm talking about the sum of the 100 Newton force and 150 Newton force about point D. What is the sum? Again, you can see I added 2 plus 3 to get 5 meters for the 150 Newton force. So that when I multiply 150 times 5, I get 750 Newton meters anti-clockwise, plus 100 times 2, that is 200 Newton meters, and that is what gave me 950 Newton meters anti-clockwise. Now, let's look at a situation where I have a system in equilibrium. Here, we were just practicing how to get the sum of the moments about a given point. Now, in this question, I have this system and it is in equilibrium. You can compare this to a common seesaw where there is a pivot, then there is a plank of wood, and then several forces are on that system. Maybe there are several weights which are acting on the seesaw. So, and this system is balanced about this point. What are the forces acting on this seesaw, on this plank? Number one, there is this F newtons vertically downwards at a distance of 1 meter from the pivot or from the point of support. There is the 100 Newton force about through this point, 2 meters from again the pivot, and there is the 50 Newton force 4 meters from the pivot. The other force which students don't see is the force which the knife edge, see this knife edge here? It is exerting a force on this plank of wood vertically upwards. Of course, we are going to make the assumption that it is a light plank of wood. When we say that it is light, and in a question, when you are told that the diagram shows a light piece of wood or a light metal rod, you know, the word light is used. It means you ignore its weight. Ignore its weight. So over here, weight is not one of them that we are going to consider. But we do know that this knife edge here is exerting an upward force on this wooden plank. Otherwise, the wooden plank would just fall downwards because of the three forces which are acting on it downwards. So, the force which is acting on this wooden peg at this point, the forces which are acting on this plank through this pivot due to the peg is equal to F plus 100 plus 50 vertically upwards. So we know its value must be equal to this plus this. Because as far as we are concerned, this system is in equilibrium. And for a system to be in equilibrium, there are two conditions that must be fulfilled. One, the resultant force on that system must be 0. And you can see I have determined that the fourth force acting on that plank must be vertically upwards so that it is equal to the sum of the three forces acting vertically downwards. In that case, the resultant force will be 0. So you can see the problem appears a bit complicated, but it is not, because I'm going to eliminate that fourth force by using a principle which I taught you in one of the videos where I taught you how to calculate moment of a given force about a certain point. We said this: if the line of action of the force acts through the point about which we are taking moments, then the distance is 0, and by extension the moment due to that force about that point is 0. That is why we will choose this to be the pivot, to be the point about which we are taking moments, in order to eliminate that fourth force, because its moment will automatically be 0. And let's do exactly that so that you can see how we go about it. So over here, hoping that you'll be able to see my pen, there is this force which is acting on that system, and we have said it is acting vertically upwards, and its value is F plus 100 plus 50 vertically upwards, so that this system is in equilibrium. So we are going to take moments about point O. So, and you're going to see that F tends to turn this system in the anti-clockwise direction, and it is the only force turning the system in the anti-clockwise direction, and its moment will be F, because we don't know how much F is, but we do know that this distance is 1, and this will be in the anti-clockwise. Let's look at this. This will be in the clockwise direction, and its moment will be 100 times 2, which will be 200 Newton meters clockwise. How about the moment due to this? It will be 50 times 4, which again gives me 200 Newton meters clockwise. The sum of the clockwise moments will be 400 Newton meters in the clockwise direction. The principle of moments states that the sum of the clockwise moments, which is this one, is equal to the sum of the anti-clockwise moments about the same point. So it is equal to F times 1. And we get that the value of F will be equal to 400 newtons. That is how you identify the unknown force over there. And you see that I've successfully been able to use the principle of moment. So play this video and see some of those points that I've mentioned. In the next video, we are going to look at more calculations involving the principle of moments. See you in the next video.